figure out what the end behavior is, figure out what the multiplicity of those zeros are, and then from that, figure out what the graph might look like. Now, we don't know exactly what it looks like. You could have sketched something like that, and that is equally correct. Right? It matches the right end behavior, it matches the right zeros, and it matches the right behavior at each of those zeros. So those are the things that I am looking for with these graphs. Questions on this example at all?
I'm a little confused about how you found the multiplicity.
Yeah, so the multiplicity, think of it as like, it's a funny word, I guess, but like it just is saying, you know, this -3 appears multiple times. It comes from this factor and from this factor. So since there's two factors, it has a multiplicity of 2. You'll sometimes see it written x plus 3 times x plus 3 is going to be x plus 3 squared. So that's another way of seeing that this one factor has multiplicity 2 because it's squared, it appears twice.
Okay, yeah, that makes sense. Thank you.
And again, it could be cubed or to the 5th or any of those powers. Other questions?
I have a question about the graph. So if it's multiplicity 2 is going to have that bound in the middle?
The multiplicity 2 of -3 is really only impacting this little part right here within the circle. Okay, so that multiplicity of 2, I know it touches the x-axis there and comes back down because of the multiplicity 2. Multiplicity of 1 means it's going to cut right through, go from one side to the other.
Okay.
Let me give you another example. So this one I'm giving to you already factored. It'd be very hard. We wouldn't know how to factor it. In fact, it's too big and complicated if I multiplied it all the way out. But this gets at some of the same issues. So we're trying to come up with a graph for this. I like to first figure out the end behavior. In order to figure out the end behavior, I need to figure out what the largest degree term would be if I multiplied everything out. So I can see there'd be a -3, and then there'd be an x squared times an x cubed. So there'd be a total of x to the 5th. Okay, and that's because this is an x cubed piece and this is an x squared. Now there's lots of other stuff in here too, right? It's very complicated foiling to multiply it all out. But I don't care about any of that other stuff. I only care about this largest term. So that tells me that this is going to look like a negative x to the 5th end behavior. A positive odd power would be like the last one. So a negative odd power is going to look like this. It's going to come down from the left and down to the right rather than up and up because of the negative, right? And again, this would look the same whether it was x to the 5th or x to the 7th. So I know the end behavior is going to look like that. I also know the zeros, right? -2 is a 0, and the multiplicity, 2. Right here, 1 is a 0. And the multiplicity of 1 is 3. Those are my only two zeros. Right, so I know it touches, there's zeros, so it touches at -2 and at 1. I know this one starts up here on the left, and when it hits -2, because it has multiplicity 2, I know that it's going to bounce back up. It's going to come down here to 1. 1 has multiplicity 3. So actually what it's going to do is it's going to flatten out a little bit, but then cut right through. It's a small little detail, but it is something we know. It flattens out when the multiplicity is bigger than 1. But because it's odd, it cuts through. And notice where I end up here is the same of what I expected, right? The end behavior is negative, so it's going to look like this. And that's the graph we're looking for this polynomial. Questions? Okay. Okay, 1 second here. You can also go the other way, right? So I could give you a graph and you could use that graph to come back and figure out what the function looked like, right? So it's understanding how the features of the graph match up with the values and information from the function. And there's, yes, that makes sense. Do you guys don't have any questions on that?
Could you go over the end behavior one more time and how you got those directions of the arrows?
Yeah, so I know the idea here is that I know that any odd power looks like this, whether it's cubed, 5th, 7th, 9th, 11th, etc. But then a negative odd power, so this is odd, a negative odd power would flip that and look like this. And so those are sort of, I guess, facts or sort of building blocks that we got to know. And I see that, I found that here by imagining that I was going to multiply this whole thing out, but just focusing on the first term that I would get, right? Not the whole polynomial, but just the first term.
Okay, that makes,
does that
yeah,
help?
that helps. Thank you.
So other question, when do you have the multiplicity 2? How do you know that you go up or you go down for the multiplicity?
It just depends where you come from. So since this one I came from the top, it's going to stay on the top. That's the multiplicity 2. The last one I came from the bottom and it stayed on the bottom. So just from the multiplicity, I don't know. I need to combine that information with the end behavior. Okay, because it could be either one. Right, but this one I know I came from the top over here. So it has to come back up in that case. Okay. So 3.3 is working on division. And I don't want to spend a whole lot of time here while we're all together working on division. There's two types, long division and synthetic division. They're both useful and important. It turns out that synthetic division is really useful for the situations that we use most often, but it only applies to very specific cases. It's only when you're dividing by x, plus or minus a number. So if you're dividing by a polynomial like that, you can use this synthetic division. And it turns out that's mostly what we do, and it's kind of quicker and shorter. Long division, you can work, or you can divide by any polynomial, but it definitely takes longer and is more work. So it is very useful for us to know both of these techniques. Remember what happens when you divide. If I take 12 divided by 3, we get 4, and what that means, of course, is 12 is equal to 4 times 3. So one way of thinking about, and there's no remainder, right? One way of thinking about division is we're sort of looking for this number so that when I multiply it together, I get back what I started, right? Or as close to what I started as possible. So you want to make sure you're able to do that division, because we need that in order to rewrite and break apart polynomials to help us kind of factor them, right? And that becomes pretty important when we're in 3.4. So I want to make sure I talk here and introduce some of those ideas in 3.4. Hopefully, like I said, you've gotten through some of that work already in chapter 3. And there are some new strategies here in 3.4. Okay, zeros of polynomials. And the challenge for us is that, if I give you something like f of x equals x cubed plus 3x let me think about this, plus 4. Yeah, let's try that. We know some things about this. We know this is a cubic polynomial. So I know the end behavior is going to look like this. And in fact, that tells me that somewhere there's a 0, right? Somewhere, if I go from here to here, I have to connect that, and that's going to create a 0. And we know the zeros create factors. But the problem is, because of this is an x cubed, we actually don't have strategies for factoring x cubes in general. Sometimes we can get lucky, like the one we saw earlier. This one, it's not totally clear how this is all going to fit together and factor. And so what we need to do is develop some more strategies so that we are able to find some of those factors, or at least give us a chance of finding some factors, right? And there's kind of three possible types of zeros that we could end up with. We could end up with what are called rational zeros. So remember, rational zeros, rational numbers are plus or minus like 1 or 1/2 or 2/17, etc., right? So rational zeros are fractions. So that's one type of zero. It might be a fraction. Then we also have another category called real zeros. And real zeros include all the rational zeros, but they also include things like 1 plus the square root of 7 or negative square roots of 3 and lots of other numbers too. But anytime you have a square root of an imperfect square, that's not a rational number anymore, but it is still a real number. It has a location here on the number line, right? We can estimate it by taking the square root and adding it together, and that gives us a spot. And then finally, we have complex zeros. So complex zeros include all the real zeros here, plus what are called imaginary numbers. Right? And you would have seen these and worked with these in the quadratic formula, things like 3 plus I square roots of 2 or 17I, etc. Okay, so if the number has an I in it, then it's not a real number and it doesn't have a location on this axis, but it's still a number and it still can potentially make this function equal to 0. So we need to be very conscious and careful when we are looking and answering these questions. The book will ask you, find all the real zeros. And I will have students that will write down imaginary zeros in that case, right? And they may actually be the right zeros, but they're not what we're looking for, right? So we need to read and think about what these different types of zeros are and how to categorize them. It turns out when we are working with polynomials like this, real zeros here are going to come from what are called irreducible quadratics. So that's something like, x squared plus 2x plus 5. That's an example of an irreducible quadratic. And it's irreducible because I can't factor that. Right? And if I can't factor it, then the only way to find zeros is to use the quadratic formula. And the quadratic formula is going to generate these real zeros. It could also generate imaginary zeros, right? It just depends on which way it's called the discriminant, the part under the square root is. If the part under the square root is a positive, then we're going to get a real zero. If the part under the square root is a negative, then we're going to get an imaginary zero. But when you're looking at something like this, it's going to, the real and complex zeros are generated by what are called these irreducible quadratic factors. And so the next question is, okay, well, what about the rational zeros? Where do those come from? Well, it turns out there's something called the rational zeros test. And what that is that if I have a polynomial like this, if I take the factors of 4 divided by the factors of whatever coefficient is there, which is 1, and I allow those to be plus or minus, these are all possible rational zeros. Now, certainly they're not all rational zeros. I mean, there's only 3 possible zeros at all. And many times there's lots more possible rational zeros, but it is still limiting what we have to try. So we don't have to try like 2/32, right? 2/37 is not a possible rational zero based on this conclusion, and so I would never try it in the function. So factors of 4 are 1, 2, and 4. Right, and those can be plus or minus. So there's 6 possible factors here that are rational. Now, I don't know if those are going to work or not, right? Each of those is a possible rational zero. And so the way we want to test those is just evaluate my function at each of these numbers, right? So f of 1 is going to be 1 cubed plus 3 times 1 plus 4, that equals 9, which is certainly not 0. Right? I mean, it has to equal 0 to be a 0 because it's an x-intercept. Let's try f of minus 1. F of minus 1 is going to be minus 1 cubed plus 3 times minus 1 plus 4, that equals 0. And so you should sort of feel like jackpot, right? Like we're searching for these numbers and I found 1. And there's only 3 of them total, so I'm kind of a third of the way there. Now I could just keep searching for rational zeros, but remember, if this is a 0, then x plus 1 is a factor. Sorry, I'm off the page here, right? If minus 1 is a 0, then x plus 1 is a factor. And so I know one of the factors of my original polynomial. Write that here, x cubed plus 3x plus 4. That's my original polynomial. And so what I'd like to do here is use division. So this is where you need division. Since this is a factor, it should divide evenly into this polynomial. And when I do that division, I'm going to figure out what the quotient is, which is the part that multiplies by the x plus 1. So I'm going to break this down. I'm going to have the x plus 1, which is a linear factor, and then I'm going to have an x squared left over, right? Because together those are going to make that x cubed here. So the easiest way to do that is with synthetic division. So if you haven't done synthetic division, this might seem a little strange. You should watch the video for that. I take the opposite of that, and then I list my coefficients here across the top. So I have 1x cubed, I have no x squareds, I have 3 x's, and I have a 4. Right, and the rule is I bring down the 1 and I multiply it. I add these together and I multiply it. I add these together and I multiply it. I add these together. This is my remainder, and I knew it was going to be 0 because it's a factor, right? That's what it means. When you divide, you get nothing left over. The remainder is 0. So these coefficients, this is the x squared and the x and the constant, that tells me that my original factor times this, x squared minus x plus 4. Right? This polynomial can be rewritten as that. That's what division says. And I was able to crack it apart because I found one of the zeros. Right? That's like it's like a little, it's like a crack, right? I find a crack in the polynomial by figuring out what one of the zeros is. Then I use that crack to split it apart. And what's left then is a smaller piece that I can work with. So I could repeat the same process here. Sometimes I'd get lucky and find a rational zero, but remember this is a quadratic, so it could also generate imaginary or real zeros. So I wouldn't mess around with rational zeros test here because there may or may not be any rational zeros. I would start right in with the quadratic formula. So let's see what I have. X plus 1 times x squared minus x plus 4. So negative b plus or minus the square root of b squared minus 4ac all over 2a, right? A is 1, so I don't need to worry about that. 1 plus or minus the square root of negative 15 over 2. So I see that these are imaginary solutions. They are not rational. I would have never found them by looking for rational zeros because they're not rational, but they are zeros. These are values that make this quadratic equal to 0. That's what the quadratic formula tells us. And there's 2 of them. I knew there was 2 of them because it's a degree 2 polynomial. And if I wanted to, I could write this out now. X minus 1 plus I square roots of 15 over 2. And x minus 1 minus I square roots of 15 over 2. Right, whatever the 0 is, x minus that 0 is a factor. So this is my polynomial that I started with, broken down into its 3 linear factors. Every polynomial can be broken down into these linear factors, x minus, x minus, x minus, for they're equal to the degree. This one has 3 different zeros, right? But only one of them is a real 0. So these imaginary zeros are not x-intercepts. They're not where the graph touches the x-axis at all. So if I were to sketch this one, sometimes you're not asked to sketch these. These are, there's some other things going on here. It was x cubed plus 3x plus 4 was my original polynomial. So I know my end behavior is x cubed. There's a 0 here at minus 1. It has multiplicity 1, so it just goes right through. These are imaginary zeros, so we don't have to sketch these. The graph doesn't come down and touch the x-axis again. What actually happens is that it does this somewhere else. And that's a sort of a observation for a different class or a different time. Typically with these kinds of questions, when you're dealing with imaginary solutions, we're not concerned about the graph as much. We're interested in maybe the complete factorization or what all of the zeros are, right? Those are more typical questions here for this type of problem. So just to recap here, I made it look a lot longer than it really was because I described kind of what the different types of zeros are. But we start with a polynomial. A good place to start is the rational zeros test. So I said, okay, what are the possible rational zeros? And I just started checking them. As soon as I found one, I figure out what the factor was so that I can divide and cut this into 2 separate polynomials, right? They're each going to be smaller and easier to work with. As soon as I get to a quadratic, I use the quadratic formula to split that one apart. I want you to be very careful about what you are answering. So this is the factored form. These are 2 of the zeros. Minus 1 is the 3rd zero. So if it asked you for the zeros, I would write this. If it asked me for the factored form, I would write this. Okay, they are very related to one another, but they're different things. Okay? As soon as I know the zeros, well, I can just take those and put them in here to get my factored form. And if I needed to find my original polynomial, I could multiply these all together. It would be a little bit of work algebraically. It turns out it's a lot easier to multiply these two together first, because when you do that, it's going to simplify down to that quadratic. So this form magically reduces to this quadratic. It's not magic. Questions there? These are big problems. In some ways, they may be the hardest problems that we do, just because there's a lot of ideas about how we go about and do things. They're not the hardest in terms of the algebra that we're doing, but the sort of why it's working is, it takes some thinking. It's a new way of looking at these problems and these polynomials. Questions?
I think I have one about the homework.
Sure.
That is for that point, number 3.
Within the 3.4?
Yes, 3.4, number 3.
Yeah, let's take a look.
Thank you.
Oh, the number of zeros?
Yes.
So the number of zeros is always equal to the degree. So if your polynomial is this, it's degree 6, it's going to have 6 zeros. Okay. Now, finding what those zeros are can be a lot of work, especially with a bigger polynomial like this, right? But I know that there are 6 zeros. Some of them might be real zeros, some might be rational, some might be imaginary, but there's 6 of them. So what that means is, I can eventually pull the 7 out, but I'm going to get 6 linear factors. One of those for each of the zeros that I find. Okay. Other questions?
And the next one that they say they use the rational zero test. I understand that is like something like that, but I don't get it, how to do it.
Yours may be different numbers than this. But what the rational test to list the possible rational zeros. So remember, the possible rational zeros include all the rational zeros, but also usually some other ones that don't turn out to be rational zeros, but it's still a limited list. And the way we come up with that list is we take all the factors of the last term and we divide them by all the factors of the first term. So the factors of 15 are 1, 3, 5, and 15. And the factors here are 1 and 2. So I could have 1 over 1, 3 over 1, 5 over 1, or 15 over 1. And I can have a positive or a negative. And then I can have 1 over 2, 3 over 2, 5 over 2, 15 over 2. Sometimes these will be the same, right? Like if it's 10 over 2 and 5 over 1, well, then I don't need the 10 over 2, right? I've already got that one. But in this case, they're each different. So I end up actually with 1, 2, 3, 4, 5, 6, 7, 8, and they can be plus or minus. So there's 16 possible rational zeros. It'd be a whole lot if I had to actually check all of
Yeah.
those.
I was wondering that if you need to check to know what is the series, because I think in some points they told you like find a series and then make the division.
Yeah, so yeah, sometimes you will. This one would be much larger than one that we would normally see. So you can't, we wouldn't test that typically. But yeah, some of them could have like 6 or 8 zeros in them. The chances are, if there are rational zeros, you'd be very unlucky if you had to go through like all 8 of them. Typically it's the first couple, you'll probably find one of the zeros, and then that'll help you start to break down, right? Or split the problem into smaller pieces.
Yeah. And is any, I don't know, sometimes I feel like I can mess it up easy in that points because sometimes you forget the number. So, but is any way that you can check your job in that stuff?
That I can check that I've got the right zeros.
Yes.
I mean, yeah, you just got to list the factors. I mean, I guess you can count them, like here, there's 4 here
Mhm.
and 2 here. So I know that's going to give me 8 possibilities, right? 1, 2, 3, 4, 5, 6, 7, 8. So I know I've sort of written down all the possibilities. Okay. So there was a question about the long division. Let's divide x cubed plus 5x minus 7 by x plus 2. This one I could do with synthetic or long division. I can show you both ways here. If this were x squared or 2x plus 2, then I can't use synthetic division anymore, and I have to use long division. And so we set up long division just as you would kind of long divisions by numbers. Notice I left a little gap there for the x squareds because I kind of want some space in case I need some x squareds, which I will in this problem. And so what you do is you pick something up top so that you can multiply it by x plus 2 and match up with this x cubed. So in this case, we need an x squared because x squared times x gives me x cubed. That's what I want. X squared plus 2 is 2x squared, which just is what it is. I don't want it, but it's there, so I have it. It comes along for the ride. So then I subtract both of these, and those should always cancel, which makes my problem small. And now I repeat the process. What times x gives me minus 2x squared? Well, I need a minus 2x. That gives me minus 2x squared. It also gives me a minus 4x. So just like before, I subtract, so that means changing the signs. And that's going to cancel. 5x plus 4x is 9x. What times x gives me 9x? Well, that's 9. 9 times 2 is 18. Change the signs. And cancel. That gives me minus 25, and that's my remainder. Right, so x plus 2 wasn't a factor of that because there's something left over, right, a remainder. If I were doing it by synthetic division, what we do is we put the opposite of this number here. If it was minus 2, it'd be plus 2. If it's plus 2, it's minus 2. And then I list just the coefficients here. I guess like the last one, it's missing an x squared. They're not always like that, right? Sometimes they're missing an x, sometimes they have all the terms. But if it's missing something, I need a 0 there. That's important. And then the steps are I bring the numbers, I add the numbers, and then multiply. Add the numbers, multiply. Add the number. And you can see, right, I end up with the remainder here. So this is the remainder. And you can also see here, it's 1x squared minus 2x plus 9. That's what this 1 minus 2 and 9 tell me. So either one of those, right, is going to give us the same result. You can see that the synthetic division is quite a bit faster and easier, but you do have to set it up right. Again, those are pretty like quick examples. So if you haven't seen that before or haven't worked on that section, then might feel like a little crazy.
Just to go over that, so you just
Yeah.
take the x2 in the long division, and you basically multiply it to something up top. Basically, you just pick something up top to make sure it equals these, so you can like make zeros, right? Like to, what is it, cancel them out?
That's exactly right. So I'm like, when I was doing this, I'm only looking at this x cubed term here, and I'm thinking what times x will give me x cubed.
Mm-hmm.
It's got to be x squared. And then I do the multiplication, and like you said, I pick that so that it cancels out that first piece.
Okay.
The two errors that students make in the beginning, sometimes students are so focused on the first terms they forget to also multiply the x squared times the 2, right? So that's one mistake. But the more common mistake is that people mess up the signs. So notice I did it in red here. That's what I like to do, and it tells me to subtract, right? And subtracting just means switching the sign and adding. That's the same as subtracting. So every time I do the multiplication, I then switch the signs and add them together. So that's the number one mistake that people make, even when they know kind of the process. They just forget to keep track of the signs, and if you make any little error throughout the process, everything else gets thrown off.
Okay. Thank you.
Yeah. Other questions about either of these? Yeah, go ahead.
But I going to ask you about the last, about the number of zeros. So if P is minus 63, do you take the minus 63 or you just get 63?
For like the rational zeros?
Yeah, for the number of zeros.
Well, so the two different questions. The rational zeros are where we list all those different fractions. And for that one, it doesn't matter whether you take the positive or the negative 63, because you're going to get both the positive and the negative of all the fractions. So each fraction you write is both a positive and a negative, so you don't have to worry about the signs for that. So yeah. Other questions? Any other homework problems or? Okay.
Wait, can I
Yeah.
ask why does that make -2 squared x like yeah -2x like -2x squared when and then -4x, like why does it make that? Yeah, why
Like
does it?
in here.
Yeah.
Okay. So the x squared times this gave me the x cubed plus 2x squared.
Mm-hmm.
And
Yeah.
then I subtract both of those, which gives me a negative 2x squared. So like when I subtracted each row, I have to distribute it to however many terms are here.
Mm-hmm.
So, okay, so I've got a negative 2x squared, and then I just bring these pieces down.
Mm-hmm.
So now I want to get a negative 2x squared here. So it's negative 2x times x is negative 2x squared. And negative 2x times plus 2 is negative 4x.
Oh, okay. I was confused. Never mind. Sorry.
Does that, no, that's a good question, because that's like I was saying, that's right at the kind of stuff where I see most of the mistakes. Because it's easy to lose track of positives and negatives in there. So you need like some sort of, these are both very like procedural problems, meaning like I'm not thinking really about these. I'm just like a robot, right? I do this step and then I do that step and then I continue. Right, same here. I'm not like looking, there's no sort of deeper meaning to this. This is just a process that spits out the answer that I want. Okay, and it's really the same thing here. I'm not looking at some sort of deeper meaning or connections like we are in other problems. Most of the time we are, but with these division problems, I just want to get the process down so that it can sort of spit out the right answer for us.
Okay.
So even if the sign is negative, so -4x, you still add another negative, which makes it positive.
Yeah, so the subtraction is the same as adding the opposite. And, you know, you do that when it's written in like a normal form, no problem. Here it maybe feels differently. So the rule is you change the sign and then add. That's an easier way of doing subtraction. So like you said, if it's a negative, it becomes a positive. If it's a positive, it becomes a negative.
Okay.
At when I combine, right, this stage here. And you guys are asking good questions, because that if you can figure out sort of how this works at one stage, then you've got the whole thing, because it's just the same all the way through. But until you figure that out, it's like it looks like there's a lot of confusing pieces in there, right? So we got to understand where those are coming from.
For the synthetic division, so the 0 came from the -2 and the x plus 2?
The 0 here came from this original polynomial because it's the x squared. So there's no x squareds in this problem.
Okay, I see what you're saying. Thank you.
So if I were dividing, say, let's divide x cubed minus 8 divided by x minus 2. So what I would do then is I would put a positive 2 there. I have 1x cubed, no x squareds, no x's, and a negative 8. So I bring down the 1, 4, 4, 8, and I add those together. And this is a factor then, right? Because there's no remainder. This is my x squared x constant. You actually go the other way because there could be more terms out here, but this is the constant and the x squared, x cubed, x fourth, however many other terms there are. right? So that tells me that my divisor times this quantity, because there's no remainder, equals that x cubed minus 8.
Thank you for that. That makes sense.
Good. Yeah, I think sometimes, like, you know, so if you're feeling a little lost on this, go back after class and just look at one or two of the examples on D2L, even just the short examples, you know, that I made up. And I think seeing another example, you'll start to be like, ah, okay, I see why these parts are going together. And if not, of course, ask me, because you do need to be able to do this in order, like we said, to kind of break the polynomial down, right? Notice this division, right, allows me to take this x cubed minus 8 and factor it, basically, right? And then this piece here has another 2 factors, but I don't know what they are. I'd have to use the quadratic formula, right, to figure out what those are. Okay. Any other questions?
Yes, I have one for the quiz number 13.
The quiz?
So I think I'm lost because what I should do first.
So for number 13, it says find the rational zeros of the function. So you would start by figuring out what the possible rational zeros are. Turns out in
PQ, the beginning of the equation, and the factor of the beginning of the equation and the factor of the last.
yeah, you take the last piece divided by the first piece.
Okay.
So then you'll get, you know, maybe, I think in this one, maybe there's 4 possibilities. And so you just check them. You just put each one into the function. And if the function equals 0, then it's a 0. If the function doesn't equal 0, then it's not a rational 0.
Okay. Thank you.
Yeah. So, you know, a lot of times the question will tell you what they're looking for. If it just says find the zeros, that rational zeros is a good kind of starting spot. It gives you at least some things to try to start to break it down. There are other strategies. If you look in the book, there's something called Descartes' rule of signs, and there's some bounds on zeros. I stay away from those. Not that they're so hard, they're just a lot of extra effort for not a lot of benefit. So don't worry about those strategies. We're really focused on the rational zeros. And I guess one other fact I should mention, just because it came to my mind, imaginary zeros come in what are called conjugate pairs. So what that means is if 2 plus 3i is a 0 of a polynomial like this, then it turns out that its conjugate pair, which is 2 minus 3i, is also a 0. Okay, and that's because these imaginary zeros come from the quadratic formula, and the quadratic formula creates conjugates because it's like plus or minus the square root. So it's always going to be kind of the same thing, one positive and one negative. So that's a useful fact. If you know one imaginary zero, you know the other imaginary zero because they come in these conjugate pairs. Okay. All right, so we're gonna wrap up here for today. I certainly anticipate that there'll be more questions as you work through the rest of these topics. I would strongly encourage you to try and get through everything by the early part of the weekends that you have the first part of next week to do a little studying and preparing. This material will certainly be a significant part of the exam, but also the things from chapter 1 and chapter 2 that we went over, right? So, and those topics, remember, are listed on the review information. So, I hope to hear some questions from you over the next couple days. And then I will plan to see you at your selected time this coming Wednesday.
Quick question.
Yes.
Are we gonna have like a review for the test or no?
So I posted some review tests online and their keys. And I posted a list of topics that are covered, but there are no sort of extra review assignments.
Okay.
I think, because our course is kind of compressed, it hasn't been that long since we covered those first topics. And so that was kind of my thinking on that. But if you have some other questions or some other things that you think might help you, please let me know and we can try and come up with something.
All right. Thank you.
Yeah, of course.
Okay. Thank you, sir.
Okay.
Have a good one.
Yes, take care. Be well.
Yeah. Bye-bye.
Thank you.
Yeah, bye-bye.